we're now going to look at some real applications of the k-means algorithm. And by real application, I simply mean looking at some real data. And this is just to give you a rough idea of what it can do. And a couple of times I'll give some editorial content about like basically how amazing it is what I'll say it very simply. We'll see how that works. Okay, so the first thing is we're going to look at a very famous data set. Maybe it's too famous. It's the MNIST. So images of handwritten digits. So I think this is from the post office or something like that. And so there are some examples down here. These are people writing digits. There's some preliminary processing. You know, they kind of got them approximately straight and they got about the same size. But you know, and a human doesn't have any problem reading these. Mostly, I should add, right? You know, okay, so here are just 25 examples, and you look at them, and some are clear, like that 3 is pretty clear. That's pretty clearly a 0. I don't know if we can find one that looks pretty bad. I don't know. They all look pretty good to me. Okay, so it's a data set with 60,000 handwritten digits. These are images. Each image is 28 by 28 pixels, and each entry in that vector, so we represent it as a vector of 28 squared, 784 length, and each one gives you the grayscale intensity. And we'll take it between 0 and 1 because that's sensible. I think the actual one is between 0 and 255 for historical reasons, but we'll take it between 0 and 1. So, for example, that corresponds to a 784 vector, and we can look at it. And by the way, 0 is black, and so that vector, if you were to look at it, there'd be a whole lot of entries that are just 0, right? A few would be 1, right? Those would be the ones, whichever are the pixels corresponding to where the white is, which is where it's drawn. Those would be 1. So you can even imagine in your head what those vectors would look like. Okay. So that's a very famous, very famous data set. And these are just 25 examples to just get a picture of what they look like. Okay. So we're going to run k-means. And this is just an experiment. This is just to run k-means, right? So what we do is we take 60,000 vectors, each of length or, I guess more correctly, I should say, dimension 784. And we're going to run k-means on it. And that's it. And we're going to ask for 20 different, partition these into 20 different groups. Now, I want to add something about this before we get into what actually happens. I mean, you and I know that that these are images. They're two-dimensional images. We know what digits are and things like that. K-means is profoundly stupid. It simply sees a vector of numbers between 0 and 1, which are grayscale levels. It has no idea has absolutely no idea what a digit is or anything like that. Okay, so that's just going to mention that. Okay, so, and we run it 20 times with different initial assignments. And the convergence is shown below, right? And so, here, this is just 3 of them. I think this red one is the one that ends up with the worst clustering objective if we were to blow that up. And the blue one ends up with the best clustering objective, at least the best that we found in our 20 runs. I should add something here. This shows you immediately that this algorithm is a heuristic, right? That on the red run, whatever, here, you ended up with an objective and there is another clustering with a smaller objective. So it failed to find the minimum objective value clustering, right? So it is actually quite likely that the blue is also not the minimum. The good news here, though, is if it's not the minimum, it's awful close. Okay, so we'll just leave it that way. Okay, and you can see it converges in 25 steps or something like that. Okay, so here are the representatives you find. Now remember, this knows we certainly did not tell it for each digit what the digit was. Like we didn't tell it, for example, oh this one is an 8, this one's a 3, this one's a 0, that's a 4. Nothing. This is just 7. You just get a vector, which is the image. Okay, and if you take a look at what pops out, it's kind of stunning. Like like that's kind of a zero right there. I mean, so most of the vectors in that cluster actually correspond really to zeros. Um, it kind of discovered, that's a one. That's a different kind of one, right? Now, some, of course, bleed across integers, right? Like that's probably got some fours in it and some nines. But it's actually kind of cool. Like these are probably mostly fives. Um, so that's it. I had 60,000 vectors and I clustered them to 20 groups. And each one is probably on the order of 3,000. I don't actually know. I don't remember. But the point was it clustered them. And then what you're seeing here is actually the average of all of the ones in that group. And so they're sort of smoothed out. They're kind of iconic or archetypes, right? Anyway, it's very, very cool. So the only takeaway here, this actually has no particular immediate value, obviously, is just to say that here's an algorithm that took in vectors. We did not even tell them that the vectors were represented images, number one. It has no knowledge that these are images. That's number one. Um, Number two, not only does it not know that these are images, it has no idea that these were digits. Okay? So, it's pretty cool, right? And or I mean, unless you do read, let's say, whatever Hindi script, you would get something similar. That if you just took 50,000 or a million pictures of Hindi script, out would come something handwritten. Right? Out would come something that were the character. I mean, if you knew something about it, you'd say, oh, that's such and such. That's that. But anyway, I just think it's kind of amazing here that it has actually, quote, figured out that there are these groups of, well, here it had 20, but you can see that that it actually kind of figured out that some of these things are some of these are digits. Okay, so all right, so that's very. If you're not impressed by this, then you really aren't quite thinking about what's happened here, right? Um, yeah. So, or I'd encourage you to go look at those vectors and see if you can say what digit it is or something like that. You can't. That's the hint. Okay. The next one, and this is a real application now. This is called topic discovery. Well, I'll give you an example of it. Very, very elementary example, but people do things much more sophisticated. But this is already kind of sophisticated. It works like this. What we did is we took 500 Wikipedia articles. Okay, I can't remember what they were. Maybe the 500 whatever most visited or whatever they were. Anyway, we took 500 Wikipedia articles. And then we took a dictionary with about 4,500 words, 4,400 words, whatever, something like that. Okay? So then what we did is you represent each of those 500 articles as you represent it as a vector, which is the word count vector, word count histogram, actually, right? So there are going to be a lot of zeros in those vectors, right? Because if there's a zero in a vector, it means that that dictionary word did not appear in that article. And there are some, obviously there's some words like the, and, but, that kind of thing, which appear in many articles, but there's like technical terms and stuff like that appear only, names might appear only in a few, okay? So that's it. Now, I should also mention, I just want to emphasize how profoundly stupid this is, right? So people call this a bag of words model or bag of words method. And the reason it's a bag of word method is because we take these Wikipedia articles, they're written in English, right? So there are actually, there's words. Those words have meaning. They're organized sequentially into sentences, which are organized into paragraphs and maybe even sections. So the point is, we read them and we understand what it means and things like that. So this thing is so dumb, it destroys sentences. There is no sections, there are no paragraphs, and it's simply it actually just tells you how often words from a dictionary of 4,400 different words, how often they appeared. That's all it does. So you could never reconstruct an article from it or something, or you definitely could not, right? I don't know. Okay, so that's it. All I'm doing is saying how dumb this is, right? It's pretty dumb, and you could easily imagine nothing good is going to come of this because it's ridiculous, right? How could you partition Wikipedia articles if you actually do not know the meaning of words and have like destroyed the order in which the words appeared in the document. Okay, all right, that's my preamble. All right, so we're gonna run we're gonna partition into into 9 groups. So we have 500 articles. We're gonna partition them into 9 groups, and what we'll do is we'll run k-means 20 times with 20 different initial assignments. And what we'll do is here's the convergence for some of these. There's a couple of them. I think that's the worst one. The blue is the best one, and this is just another one. But there's 20 of them. I'm only showing you 3. And so the point is we take the best clustering. Oh, by the way, notice that the difference between the best and the worst is the difference between 6.9 and whatever 7.2, right? So not a huge big deal. Okay, so now we have partitioned 500 articles into 9 groups. Okay, and remember how dumb this is, right? That k-means has absolutely no clue what those words mean. Nothing else. It just looked at word counts and got 20 groups of vectors there. Okay, and we'll see what happened. And we also have then 9 representative vectors. Each of those is a vector of dimension 4423, and it's a word count. It's like it's a word count histogram. Literally, it says here's a representative article, and here's what it looks like. Okay, so let's look at clusters 1 to 3. Okay, so what you can do then is let's look at the cluster representative. So that would be, let's look at Z1. That's a vector with 4,400, about 4,400 entries, right? And we can look at the largest entry. We can also look at the small. Well, the smallest is going to be about 0. But we're going to look at the largest entry, the largest few entries, to see what's there. And here's cluster 1, and here are the 5 largest entries in that vector. Okay, that's it, and they're pretty interesting, right? And these are, by the way, directly interpretable. 0.038 means basically 4%. So, but look at the words; they're super interesting. It's fight, win, event, champion, fighter. Okay, so we recognize these as words as being related. Okay, so we do because we understand English and we know what these words mean and things like that. Please remember this algorithm has no clue what these words mean, not even the slightest. For these are just numbers. Like fight is word number 2173. Win is word number 1725. I mean, that's all. It knows absolutely nothing else. So it's kind of amazing that this is what came out. Okay, now for cluster 1, we could do something pretty cool. So, I mean, you already have a rough idea of what the things in cluster 1 are going to be. But what we can do now is we can actually go back to the Wikipedia pages, and we could say, show us the articles that are closest to say, for example, the cluster 1 representative. And here are the titles of the articles. This is in order from the closest to, maybe it's the first 10 or something. I don't know what it is. Okay, so they are Floyd Mayweather Jr., Kimbo Slice, Ronda. Actually, I don't know who, but I think it has to do with boxing. So not that I would know. But the point is, it kind of makes sense. Like, wow, it actually kind of figured something out. I mean, something emerged, right? So that clustering is, I don't know what this has to do with, like boxing or something. Okay, fine. Let's look at cluster 2. Cluster 2 is, we go over here, and here are the words, the words that have the highest value in Z2, okay? And they are holiday, celebrate, festival, celebration, calendar. And once again, we recognize these as related, okay? So we recognize, but the point is this thing knows absolutely nothing. I mean, so, okay, so it's clear what this is. Let's look at the articles that are closest to that representative. They are Halloween, Guy Fawkes Night, Diwali, Hanukkah, Groundhog Day, Rosh Hashanah, Yom Kippur, Seventh-day Adventist Church. I don't know how that got in there. That's fine. Remembrance Day. Okay, fine. So it's kind of cool, and it makes sense. I mean, this makes a lot of sense, right? Okay, and the third one is it's got United Family, Party, President, Government. So, and then these would be the kind of things you'd see. Mahatma Gandhi, Sigmund Freud. I don't know how Sigmund Freud got in there, but okay, fine. I don't know. Frederick Douglass, okay. Christopher Columbus, Fidel Castro, okay. I don't know, Jim Webb next to Fidel Castro, okay. Okay, so let's look at like, uh, oh, sorry, I should mention one thing. Um, in this case, what we say is that a topic has been discovered. So we would say that cluster one is a topic in our corpus of documents. And it has just been discovered using nothing but vectors and distance and the k-means algorithm. That's all. It completely discovered. It just discovered it, a topic, right? So it's actually kind of cool. Okay. All right. So this is the idea there. Okay. For the next clusters, again, they all kind of make sense, right? The first one clearly has to do with singers and singing and things like that. Cluster 5 has to do with sports, and it just figured it out. Just figured it out. Cluster 6 has to do with, actually these are TV series, which is actually kind of interesting because we're going to see later that that movies are a separate one. Okay, so here's clusters 7 through 9. Things like match win, championship, team event, and cluster 9 is film, million, release, star, character. And then here are the Wikipedia pages closest to that cluster representative. Okay, so we can do some crazy stuff now. For example, we could automatically classify new Wikipedia pages. So somebody makes a new Wikipedia page, and let's suppose we stuck with these nine topics, right? Because these are, it's clearly they're all topical, right? So if we stuck with these 9 topics, and a new Wikipedia page, every day lots of new Wikipedia pages are made, right? And so what you do is you simply do the following. You calculate, you scan the words, count the words, you get its histogram, and then you simply say, which of our 9 representatives are you closest to? And we're assigning you to that topic. Yeah. Oh, by the way, I should say that when people really do this, there's usually a cluster associated with, I don't know, or not any of the other clusters, right? It's kind of like everything else. It's the catch-all cluster. But nevertheless, and now it's just completely automated, right? So that just works this way. It would just kind of go through and stuff like that. So, okay. And again, I want to say that if you're not impressed by this, then you're not really understanding what it is. And my point here is that based on shockingly little about each of these Wikipedia articles. In fact, all we tell you is the fraction of times 4,400 words came up, right? So I want to say it again because it's worth repeating. This algorithm has no idea what the meaning of these words are. None. Zero. It doesn't understand English. We have destroyed the sentences. There's no paragraphs. There's no syntax. There is no meaning. And yet, it has actually it has grouped these Wikipedia pages into what we recognize. We do understand all those things, and we recognize that these are reasonable clusterings. Right? So it's actually very, very interesting what's happened here. And in fact, it's almost like it's a hint about the material of this class, is that a lot of times stories start with things that are just ridiculous, like I'm going to simply count the number of words in documents, and I'm going to do something's going to happen, like I'm going to cluster them, or I'm going to make a prediction, or something like that. And you'd say, "Oh, that is so unsophisticated. You don't even know what the words mean. How can anything good come from this, right?" And the answer is, stuff comes out. So that's kind of a theme of the class.